1 second, it's almost streaming. Yeah, I think it's streaming now.
Cool. So today we're going to do some problems about sets, and we're also going to go over 2 or 3 questions on the quiz 2. So let's begin. The first one is element-wise proof. So let A and B be sets and U is the universal set. So given element-wise proof for this implication, if A intersects B is A, then the complement of A union B is the universal set. So we have the implication here. Oh, what's happening? A intersects B is A implies the complement of A union B. Ooh, okay. Is the universal set. So what is the general strategy we use for proving set equality? Anyone want to answer? Okay, so we first assume A intersects B is A. So we're trying to prove this equality, that the strategy we're going to use for proof set equality is show that they're a subset of each other. So we can separate this as proof 1, where I want to show the complement of A union B is a subset of the universal set. And the second one is going to be show that the universal set is a subset of the complement of A union B. Okay, so as always, let X belongs to the union of these two sets. And what we're going to do next. Anyone? Okay. So X belongs to the union of the complement of A union B basically means that X is in the universal set, right? Because the universal set means like all the, it contains all the elements. So actually we have done this proof, thus we can say and that's for proof 1. And proof 2 is let X belongs to the universal set. And then how are we gonna start from there? Because we want to show X is also in the union of the complement of A and B. Like what does X belongs to the universal set implies? Wow, you guys are so quiet today. So we have a universal set here. And the assumption right here we have is A union B is A. And what does this imply? So you have a set B here. A union B is A actually means A is a subset of B. so that all the elements in A are also contained in B. So as we go back here, X is in the universal set. We can say X is either in A or X is in A complement. Is that correct? So right now we can do the proof by cases. So the case one would be if X is in A. So if X is in A, then we know that since A intersects B is equals to A, so which means X must also be in A intersects B. Okay, and that implies X is in B just by the definition of intersects. So we can conclude that X is also in the union of these two by the definition of union. And thus, in this case, U is a subset of A complement union B. So now we have case 2. Case 2 is if X is in the complement of A. So if X is in the complement of A, which is automatically implies that X must also be the union of the complement of A union B by the definition of union. And then we can conclude that in this case, U is also a subset of A complement union B. All right, so it looks like we finished all the parts, but don't forget to write your conclusion. Always remember to write a conclusion whenever you're doing a proof, like therefore, or thus, hence, whatever. And if you want, you can draw a little box here. Okay. So we're done with the first one. Any question?
Can you explain how you chose your subcases for proof 2 to be A and A complement?
Yeah. So one possible way is using if X is in A or X is in the complement of A, or you might think about, oh, I can use if X is in B or X is in the complement of B. But since A is a subset of B, so if X is in the complement of B, we know nothing about like the relationship between, we know nothing about the relationship with A. So we're here, like we're given X is in the universal set. So that basically means X is either in A or X is in the complement of A. Because you actually want to show that if X is in the union of the complement of A and B. We kind of like to, just to create, well, not like create, but just to use the fact that we're providing here. Is that like make sense at all?
Yeah, it does. Thank you.
Okay. All right. So the next one is using the proof by contradiction. So just a quick question. Like this two, the intersection of these two sets is empty set. How would you name these two sets? Like they are, anyone know?
Be disjoint, right?
Yeah, yes, they're disjoint. So, okay. So if we want to use proof by contradiction, which, why is that? So which we want to assume actually exists elements in the intersection of these two. Okay, so now, so we assume X is in the intersection of these two sets. And just by the definition of intersection, we should know that X is equal to 2k plus 1, and X, it also equals to 4k, where your k is a non-negative integer. Okay, and then we can, okay, so I think we're actually gonna use a different variable here instead of using the 4k. Let's see. Let's say just use L. So why are we gonna use a different variable? So if we look at these two sets, they have 2k plus 1 and 4k, like k is non-negative integer, but that doesn't mean that k is the same number. So there are two different sets. So the k, you can say that 2k plus 1 equals 4k means that k, you cannot, it doesn't mean that k equals to k here. So they can be the same or different. So that's why we would just want to use another variable to be more clear. And then we can say 2k plus 1 is equal to 4l. So how are we going to start from here to actually show that this is a contradiction?
Could you divide both sides by 4 to show L is not a natural number?
If we do divide by 4, both sides, let's see what we get. So we have, okay. Is that what you mean?
Yeah.
Okay. So now we have, so we know that L is a non-negative integer. So it might seems like the k over 2 plus 1/4 is not an integer, but we don't know about the value of k. So
I have an idea.
uh-huh.
All right, so start with the equation 2k plus 1 equals 4l. Subtract 2k from both sides.
Okay, let's do that.
And then divide both sides by 2. And then by integer closure under addition and multiplication, 2l minus k is an integer.
Okay. That is the correct path. So by closure of the integer, to L minus K. So we know the difference of two integers must be an integer. And 1/2 is not an integer, which give us a contradiction. And then we can say, okay, now the original statement must be true, which means there's no such element X that belongs to the intersection of these two sets. Hence, there's no such X. And we can say, okay, the union of these two sets, the intersection, sorry, is empty set. And we're done.
We can complete the proof with a divided by 4 one too. If you just put the put 4 as the denominator, so you have 2k plus 1 in the numerator,
2k plus 1.
right? It's going to be 2k plus 1 over 4, right? On the left side.
Oh, okay. I see what you mean.
Yeah. And is equal to L. So then we know that both k and L are integers, right? But then that can't be true because 2k plus 1 is odd. It cannot have 4 as a factor or even 2 as a factor. So L, one of them cannot be an integer, and that is a contradiction.
Yeah, I think you're right. Yes, this also works. Okay. So the next one is power set problem. So let A, B be sets and prove the power set of A union the power set of B equals the power set of A intersects B. And that's another proof of set equality. So like always, we're gonna show they are subsets of each other. So, but this time, this is actually the power set. So let the set C belongs to the intersects of these two power sets. And for this proof, we're trying to show the power set A intersects power set B is a subset of the power set A union B. And now we can see that since C is in the intersection of these two power sets, so by the definition of power sets, or by the definition of intersection, sorry, C must be in both of the power sets. Okay. And by the definition, of power set, we know C must be a subset of A, because your A is also a set, and C is a subset of B. So C is the element of the power set of A, but it's a subset of A. Okay, and then we can, and which that implies C is a subset of A union B, intersects B. And which means C is one of the sets in the power set of A intersects B. And we're done with our proof 1. Okay. Proof 2, we want to show that the power set of A intersects B is a subset of power set A intersects the power set of B. So this time we let the set C belongs to the power set of A intersects B, which means C is a subset of A intersects B. Okay. If C is a subset of A intersects B, which means C must also in B and must also be in A and also in B as well. Okay, and now this implies that C is in the intersection of power set A and power set B. And then we can conclude that this is true. Therefore, the power set of A intersects the power set of B equals the power set of A intersects B. All right, any question on this one? Okay. Let's move on to the next one. We have a Boolean algebra problem. So in this one, we want to prove A plus B dot B plus C is AC plus B using the Boolean algebra equivalence of the properties below. Okay. What do you think is going to be the first step we want to, like the first property we want to use? Anyone have any thought on this?
Probably start with the commutative property.
Yes, we can use the community first. Community on which two?
I changed the first parenthesis to be B plus A dot B plus C.
Okay. And what would you want to do starting from here?
Distributive.
And then we're gonna use distributive. So do you view like the first term as a whole? Or the second?
Yeah, wouldn't that go to B dot A plus C?
B dot A plus C?
Yeah.
Oh, you're using like the reverse version of the distributive?
Yeah, I think so.
Okay, so I think we're trying to avoid using like any reversive of this property. We just want to use like because the distributive means that it's like A dot B plus C, and you use distributive, that would be A dot B plus A dot C. That is called distributive. So we just want to use exactly the same as we have in theorem. But we do need to use distributive this step. So if we view the B plus A as a whole, so that would give us B plus A dot B and plus B plus A dot C. Okay. And then what do we want to use next?
Use commutative with the B plus A dot B.
Mm-hmm. So actually, we don't need to the commutative right here, like the first step. We can actually directly use the distributive to get A plus B dot B and plus A plus B dot C. So,
Yeah. What I was saying is you could switch it to B dot B plus A,
yeah,
and then you could use absorption.
yes. So right here, there's a absorption. We're going to use the first one. And that will give us just B. And plus C dot B plus A.
Oh yeah, what's the statement we want to get to?
It's AC plus B.
Oh, okay. So we're close.
Yes, we're close. Just one more step. Or two, if we ignore the commutative. So here we have B plus C dot B plus A. And what would you gonna use?
I would use distributive.
Mm-hmm. Yeah, let's see, we're so close to the right-hand side, which is AC plus B. And now we have B plus CB plus CA. So we can probably use commutative again here.
Yeah.
And then what you can see is that the first part, B plus BC, is actually we can use the absorption here, which will give us B and plus AC. And we're done.
All right. Awesome.
Yep. Okay. Any questions? So just remember for this type of problem, we just want to use the exactly order or the exactly sequence of what is being listed in the theorem. And yeah, I think that's like the one rule you have to always keep in mind to do this type of problem. Okay. All right, so next gonna be the questions from quiz 2. So we'll just go over, I think 3 questions from quiz 2 together, like probably like the most challenging one. So this one is problem 3 on quiz 2. So I look at the statistics. They're like about 40% of you like got completely correct, and 40% like got only like less than half points. Because this question is worth 20 points. So like just I'm sure like all of you have read this question already. So anyone have like any ideas or want to share like how you have approached this one? If you did this right, or if you did something wrong, but figure out why you did that wrong. Any answer in the chat?
Nope.
Okay, so while I was like reading all the solutions, I noticed like a portion of you did this just by separating the cases as if n is even or if n is odd. So that actually cannot lead you to 3 divides n cubed minus n, because even or odd is only like 2n plus 1 or 2n. That cannot give you like anything, like contains 3. So what we're trying to use here is the case is that case 1, we're gonna use the division theorem, like n. So either n must be 3k or 3k plus 1 or 3k plus 2. That includes all the possible elements for n. So for the first case, if we say n is equal to 3k, just by substituting that into n cubed minus n, and what we'll get here is 27k cubed minus 3k. And if we factor this into 3 times 9k cubed minus k, and we know that by closure, this will give us something like 3L, where L is an integer. And now I have shown that n cubed minus n is divisible by 3 for case 1. Okay, and similar for case 2. So if we let n equals to 3k plus 1, which means it had a remainder of 1. Again, by plugging into n cubed minus n, so just a hint, it would be nice if you guys all can remember the a plus b cubed is a cubed plus b cubed and plus 3 times a squared b plus 3 times a b squared. Right, I think that's right. Yes. So if we just using that, we will get 27k cubed plus 1 and plus that's 3 times 3k squared times 1 plus 3 times 3k times 1 squared. And we still have minus 3k minus 1. Okay, and then we have, just do some algebra here. What we'll get is 27k cubed plus 27k squared plus 9k and minus 3k. And the 1 plus 1 minus 1 canceled out. And then we can factor out the 3, gives you 9k cubed plus 9k squared plus 3k minus k. And again, by closure, this is 3L. Okay. And for case 3, it should be similar. You also start with n squared minus n and substitute the 3k plus 2. So right here, I'll just skip a few steps and we will get 27k cubed plus 54k squared plus 33k plus 6. And that's after simplification. And again, we factor out the 3. And that would give us 18. 11k plus 2. Helps 3L by closure. And we're done with the proof. Just don't forget to write your conclusion. Okay. So any question like regarding this one? Problem 3 on the quiz 2. Okay. I'll just assume all of you know how to do this one. All right, and this one is 6b. And it should be obvious that we're gonna use induction. We want to show the left-hand side is equal to the right-hand side. So we start with the We know all the 4 steps of proof by induction. The first one is problem statement. Just to be like easier to use, I just want to let the left-hand side to be AN. And the right-hand side is BN. Okay. And we want to actually show that your Pn is going to be AN equals to BN for all n greater than 1. And that is our problem statement. And now we have the base case. So can anyone tell me like what is A1?
A1 would be 2.
Yes, and that's come from 1 times 2. And what about B1?
B1 would also be 2.
Yes, if we substitute n equals 1 into this equation, we have 1 times 2 times 3 divided by 3, and that's 2. So we have showed that A1 is equal to B1. And now we're going to write our inductive hypothesis. What is your, what do you want to assume for the hypothesis?
That A of n plus 1 is equal to B of n plus 1.
A of n plus 1 is equal to B of n plus 1. Is that what you mean?
Yes.
Okay. So if this is our inductive hypothesis, then for our inductive steps, we're gonna start with A sub n plus 2, and to show that is equal to B sub n plus 2. And you can do that, but it would probably be a little bit more work since you have plus 2 there. So just to be easier, I just want to assume that AN is equal to BN and show A of n plus 1 is equal to B of n plus 1 in the inductive steps. You can also start from A of n plus n minus 1 equals B of n minus 1, and then you show the AN is equal to BN in your inductive hypothesis, in your inductive steps, as long as you clarify your n. Because right here we start from n is equal to 1. Okay. So I'll just start from this one. AN equals to BN. And then for the inductive steps, we want to start with A of n plus 1. To do some algebra to eventually get your A of n plus 1 is equal to B of n plus 1. So we know that like just by the definition of AN, A of n plus 1 is just 1 times 2, plus 3 times 4 plus all the way up to n times n plus 1 and plus n plus 1 times n plus 2. Okay, that's like by definition of your AN. And just by looking at the inductive hypothesis, what can you, like, what is the next step you're going to do?
Find what B of n plus 1 is.
Yes, we want to find what B of n plus 1 is, but how can we get there? We can always use the statement right here, the hypothesis we have, this one. So what is our A of n? So you have the A of n plus 1 is equal to this chunk. And actually, if you look at this part, just discard the last one. What is this? What is like all the sum of this term? It should be clear enough. That's AN, right? And right now, by using the inductive hypothesis, we know that AN is equal to BN. That's what we assumed. So we can just substitute BN here. And then the equation of Bn is n times n plus 1 times n plus 2 divided by 3. Just by substituting that, we get n times n plus 1 times n plus 2 over 3 plus n plus 1 times n plus 2. Okay. And what are we going to do from here?
Would it just be to do algebra?
Mm-hmm. Yep. And then if you add this two together, that would give you n plus
N plus 3, yeah.
yeah, and n plus 1, n plus 2. Okay. And this one is equal to B of n plus 1. And we're done. Okay. Any questions about how we get to B of n plus 1? Okay, and I think it's time. So I think that's all we're gonna have for today.